Hello, ladies and gentlemen. We're going to do 5.3 today in a very condensed form. I think you only have 2 pages of notes, you lucky dogs. So we're going to be talking about inverse functions. We want to verify that one function is the inverse of another function. Then we want to determine if an inverse exists. And then lastly, we want to find the derivative of an inverse. So let's go back and remember some of our information about inverses. So there are 3 ways to find an inverse. And remember that the notation for an inverse looks like that. The first way would be to reflect f of x across the line of y is equal to x. So remember that I would be doing that graphically. Sorry, brain and mouth aren't working at the same speed. The next method would be to exchange your x and y variables, okay? And then in an equation, the step that most of us forget is then we need to solve for y. And then remember, you always have to report an inverse with that notation. And then the last way would be in a table of values. And that would be exchanging the x and y values. So what that would look like is if I have an ordered pair that starts off as x and y, when I find the inverse, it's going to become y and x. Alrighty? Okay, the next thing that we need to do is we need to get a definition of an inverse. Okay, so here's our definition. It says a function g is the inverse of the function f if and only if the composition f of g of x is equal to x, and I can have the opposite direction if the composition of g of f of x is also to equal to x. So the functions are not inverses of each other unless the compositions yields an x. Alrighty, a couple of things that we want to talk about just to remember about inverses, because if you'll remember, these show up on your AP exams kind of in an entertaining way. So there's some information that we need to know about the inverses. The first one is the domain of the inverse is the range of f of x. And so if you look back to here, this makes sense. So if this is the domain of the original function, then that becomes the range of the inverse. So this guy is the inverse, and this guy is the regular function. The next thing to remember is that not all functions have an inverse, but if it does, then the inverse, negative 1 of x, let me scoop my paper up, sorry, is unique. And so each function, if it has an inverse, is going to have a unique inverse. Alrighty? And then the next one would be a function has an inverse if and only if it is 1-to-1. And if you remember from previous math classes, that means that the function is going to pass both the vertical line test and the horizontal line test. So for a function to have an inverse, it has to pass both of the vertical and horizontal line tests. Alrighty, so the next thing that we want to talk about is the derivative. Sorry, get my paper straight. I can't seem to get all of my pieces lined up. So the derivative of an inverse function, my little camera thingy at home has a flexible arm and it always seems to be doing weird things. If a function has an inverse, then the following are true. And I haven't done an example of finding an inverse because I'm assuming at this point in your math life that you can flip-flop the variables and solve for y. I'm also assuming that you can flip a table of values if necessary. So if a function has an inverse, the first thing that's true is if the function is continuous over its domain, then we know that the inverse is also continuous over its domain. And if you're thinking, that would be the range of the original function. The second thing that's true is if f is increasing on its domain, then the inverse is also increasing. A lot of writing today over its domain. Okay, so if it's true for one, it's true for the other. The same thing would be true if f is decreasing on its domain, then, then the inverse is also, can't spell, also decreasing over its domain. Monkey see, monkey do. One more. Is that true? Two more. So the next one, 4, it says if f is differentiable, that's a hard word for me to spell, on an interval containing c, an interval containing c, okay, and so it would be an interval containing c, and the derivative at c isn't 0, so I don't have a horizontal tangent at c, then I know that the inverse is differentiable at f of c, okay? Alrighty, the last one says that graphs of inverses have reciprocal, that's a lot of writing, slopes. So if I have the graph of a function and the graph of g, its inverse, those two functions have reciprocal slopes. All right, the next thing that we want to talk about is the derivative of an inverse. So that would be the situation where I am trying to find the slope of the inverse. Alrighty, so I'm going to write some notation first. So f is usually referencing our original function, and g is going to be the inverse, just so I don't have to write quite as many symbols. So then that tells me the derivative of the inverse is equal to 1 over the derivative of f and the composition with g of x, okay? So sometimes on these, remember, they present in entertaining ways. And the way that they often present themselves is in a table or maybe as a point. So maybe I'm going to have the point 4, 6, and then remember that the inverse of that is going to be 6 4. So we often end up doing the math for this particular operation from a table of values, or maybe I know one point, and then I'm going to reciprocate, or sorry, that's a bad word. I'm going to create the inverse of each of those points. Alrighty, so let's do an example. So in this particular example, we're going to know that f of x is going to equal 1/4 x cubed plus x minus 1. And off on the side, I'm going to write the derivative of the inverse is 1 over f prime composition with the inverse. Alrighty? Alright, so let's just kind of manage our problem first. So the first question says, what is the value of the inverse evaluated at 3? Okay, so that's going to be my first question. So if I try to solve, so I'm going to flip-flop my variables. I have 1/4 y cubed plus y minus 1. If I try to solve, I might get x plus 1 is equal to y times 1/4 y squared plus 1. And then I go, oh no. So this is going to be fairly difficult. So what I'm going to do is I'm going to evaluate the function at 3. Okay. And sorry, I lied. So what I'm going to do is I'm going to put my equation into my grapher, and I'm going to look for a value where y is 3. So I'm going to put f into my grapher, and I'm going to look at my table for when y is 3. And just to save a little bit of time, I won't do that in my calculator because I've already done it, and so you can check to verify. But I would fix my table set, and I would have it start at 1, and I would do my change in table, and I would have it change in 1. And since this is a fairly small value, quickly you'll see that the point of f is going to be 2, 3. Sorry, my bad. Is going to be 2, 3. And that is the value of the original function when x is 2 and y is 3. So then for the inverse, because I couldn't solve for y, and that was fairly difficult, all I have to do is reciprocate. Sorry, that's still a bad word, but it sounds really cool. All I have to do is inverse this ordered pair. So it's going to be 3, 2. So the inverse evaluated at 3 is 2. So I actually really didn't have any math to do because solving for the inverse would have been difficult. The second part of this problem, and this is our last example, so lucky dogs, says what is the value of, and I'm going to have the inverse and the derivative of the inverse when x is 3. And so I'm going to remember this point, and I'm going to put a box around this point as well. So now what I'm going to do is I'm going to use that formula that I wrote at the top of the page, which says g prime of x is equal to 1 over f prime of g of x. Okay, and then if I substitute in my values, right, so I'm going to say that the derivative of the inverse evaluated at 3 is going to equal 1 over f prime when g of x is 3. Okay, so I'm going to do g of 3. All right, so I have a little bit of math that I need to do. So first I'm going to rewrite my function so you can see it down here. And I had x cubed plus x minus 1. Well, the derivative of this little guy is going to be 3/4 x squared plus 1. So that's my derivative. Okay. If I evaluate my derivative, alrighty, sorry, so let's go to here. So now I have the inverse of the derivative of the inverse, and so down here I have the composition. Well, remember g is the inverse, and remember when we switched our points, we had the point 3, 2, so then this is 1 over the derivative of the original function evaluated at 2 because g of 3 was 2. Well, now all I have to do is evaluate my derivative at 2. So then this is going to be 1 over 3/4 times 4 plus 1. So this is going to be a quarter. So then if I rewrite my solution as they've written it in the original problem, the inverse and the derivative of the inverse evaluated at 3 is 1/4. So this is a very handy dandy. Let me move my page back down so we can talk about it. This is one of those really important formulas that you need to remember. And if you remember the way it says is the derivative of the inverse is 1 over the composition of the derivative of the inverse. Alrighty, that's it for today. I will see you tomorrow.